Okay, so you have your base n multiplication tables done. Let's take a look at what you did. Make sure that you've got it down right. Here's for base 2. We only had 2 digits, 0 and 1. So you put that across the top and across the bottom. And there we have our perfect squares down the main diagonal and the beautiful symmetry across the main diagonal. Not terribly challenging there. So now we look at base 3, and we have 3 digits, 0, 1, and 2, across the top, down the side. And so when you look at the perfect squares and the multiples of 2, you get the same values that we've seen before. 2 is the highest digit that you can have in base 3, and we see that those non-zero multiples of 2 have answers that add up to 2. And you can see this also if you did skip counting across for your base 3 multiples of 2. We see we start with 0 because all columns start with 0, or all rows start with 0. And so when you skip count 1, 2, you say 1, 2, and you see a 2. And then when you skip count again, you say 1, you skip your 1 step, 1, 2, but we recycled, so that's 1, 0, 1, 1, and that's telling you what 2 times 2 is. And you can check that because you know how to convert it to base 10. We know that 1, 1 in base 3 has 1 of value 3 in the place value 3. We have 1 in place value 1, so 3 plus 1 is 4. 2 times 2 is 4 in base 10, or 1, 1 in base 3. The next thing we want to look at is for n equals 4, and we see the same perfect squares down the main diagonal. We see the beautiful symmetry, and 3 is the highest digit. 4 minus 1 is 3. That gives us all the non-zero multiples of 3 have digits that add up to 3. When we look at n equals 5, the same sort of situation, the perfect squares down the main diagonal. And it's even clearer now that when you're looking at multiples of 4, once you get past the 0, you think 0, 4, 1, 3, 2, 2, 3, 1. The digits are counting from 4, 3, 2, 1 in the ones place, and in the fours place, it's 0, 1, 2, 3. And so they continuously add up to 4 along the way. So you could skip count your way through all of these, and you can spot check your way through. 4 times 4 in base 10 would be 16, where in base 5, this is 3 in place value 5. So 3 times 5 is 15, plus 1 is 16. There's a quick check that way. Now there's one other thing I want to show you, one interesting pattern, and there are others, but this is the one I'm going to show you. So I want to take you back to the base 10 table. So here we have the base 10 table. And I want to point out something you're really familiar with in base 10, and that is multiples of 5, or skip counting by 5s. We see it goes from 0, 5, 10, 15, 20, 25, 30, 35, 40, 45, and so on. It keeps going up that way. And the reason that we have this from 5 and then to 1, 0, and then 5 and 2, 0, and then a 5 and a 3, 0, and a 5 and a 4, 0. The reason we have this is because, or is that, the reason is that 5 is half of what our base is. So our base is 10, 5 is half of that. If you think what we're doing when we're skip counting is we're just, in base blocks, we're putting together groups of 5 blocks. So when we push together 2 groups of 5 blocks, they fuse together to form a long, so that gives us the 1, 0. Here we have 1 long and another group of 5 blocks, 5 singles. And so here we've pushed in another group of 5 singles. Those 2 sets, from the one set of 5 from here and the next set of 5 that we bring in here, push together to make a long, which tells us that we have 2 longs. So we keep doing that. Every 2 skips of 5 bring us to another long, and that is because 5 is half of the base that we're in is 10. So let's look at base 6. and see if those same patterns hold. So we have our perfect squares down the main diagonal. We have the beautiful symmetry. We see that as we're looking at the highest digit, n equals 6, so n minus 1 is 5. The non-zero multiples of 5 all have digits that add up to 5. We see the ones place counting 5, 4, 3, 2, 1. We see the fives place counting 0, 1, 2, 3, 4. But when we think about n equals 6, half of that is 3. And we see that when we look at multiples of 3, it goes 0, 3, 1, 0, 1, 3, 2, 0, 2, 3, and so on. And that's because when we push together those groups of 3 singles, we know that when we push 2 of those groups of 3 singles together, they fuse together to make one long, and that gives us the 1, 0. And then another 2 groups gives us 2 longs, and so on. And we see the same thing for base 8. The perfect squares down the main diagonal, the beautiful symmetry, the digits of the last digit, n minus 1 is 7, so all the multiples of 7 have digits that add up to 7. You see them, the ones place counting down from 7 to 1. The eights place counting from 0 up to 6, just for these digits. And if we think of what half of 8 is, that's 4, and we see the pattern 0, 4, 1, 0, 1, 4, 2, 0, 2, 4, 3, 0, 3, 4. So now that you know all of these patterns and interesting things that we're doing and that we can see with these different bases, I want you to get out the base 12 table and start working on that. And remember that in base 12, we have 12 digits. So 0 through 9, and then A, and then B. So you write that across the top, and you write them down along the left-hand side of the table. But look, base 12 is a big table. You don't have to fill it all the way in. We can use the symmetry that we know to help us fill out the table. So I want you to do the main diagonal, the perfect squares, and I want you to fill out the upper half. If you want to fill out the bottom half, that's fine. But we know from symmetry how to fill out the upper half, and that it reflects down to the bottom half. So I want you to fill that out. I want you to look at the last digits column, the multiples, the non-zero multiples of B. And I want you to notice that when you're at the non-zero multiples, you think of them as 0B, and you know that they're going to count downward by 1 each time. And I want you to count the 12's place upward by 1 each time, and see what you get down here in the bottom right-hand corner, the perfect square of B times B. And I also want you to look at what the halfway place is for base 12. That's 6. And I want you to look across the 6th column, or the 6th row, I'm sorry, and look at the multiples of 6 and see how they work as you are going across those multiples, and think about the base blocks as you are doing so.